Hello and welcome to DVCon 2021. My name is Chuck McClish and I will be presenting my paper Bi-Directional UVM Agents and Complex Stimulus Generation for UDN and UPF pins. So as for the motivation for this paper, it all comes down to the fact that driving analog pins is hard. And as the meme says to the right, one does not simply drive analog pins. For example, things are not typically on or off. A lot of times it matters how you get there. So it could be an RC function, it could be a linear ramp, and it may be an on or off step, but in that case, does the slew rate matter? So for example, in a power management block, you may need to model BORs and PORs, and the supply ramp needs to happen in a predictable fashion so that the models can react appropriately as they do in the real design. In addition to what you're driving, it also can be bidirectional. So that same block may have a test pin that needs to output a bias current, where in another case it may need to feed in a reference voltage. So that same pin needs to be able to handle inputs and outputs at different times based on how you've configured the part. And then finally you have stimulus for multiple model types. So whatever agent you build needs to be able to handle whatever UDN type you are developing, since different levels of complexity need different types of UDNs. So for example, at an IP level, you may have a very complicated structure where you're wanting to test a lot of functionality, whereas at the SoC level, where you're using this thing, it may just be a simple scalar real or even just a logic value. So you need to have an agent to be able to handle all these different types. I want to be able to leverage UVM for these analog pins. So all the goodies that come along with that, including constrained random stimulus, real coverage, standard agent infrastructure. I want to be able to write sequences that can be reused and extended. So all the goodies with UVM I want to use here. And in addition, if I do all this work for UDNs, I may as well apply this to UPF as well, because UPF has the same types of requirements in terms of voltage ramping, coverage collection, etc. So the paper is broken into three parts, and the first part is describing a function generator library. So this is the first slide we'll see here, and this is the base class. So this base class has a couple properties. The one that matters is the start time. So this records the $real time of when this object was created. Then there's a method called scaled time, and this method subtracts the current time when the method was called. It will subtract the start time property that we recorded when the object was created. And one thing to note is $real time automatically scales its value with your time unit and time precision. So on all of our models, to make it easier, we do everything with 1 nanosecond, 1 picosecond as our time unit and time precision. So in order for the math to work out, we had to scale this output to nanoseconds as well. And then finally, at the end, you have this get value pure virtual function, and all of the function generator objects that we extend from this need to define this. This is where all the heavy lifting takes place. So to give an example of how to use this base class, I've defined a sine wave generator here. And you'll see it has all the different properties required to generate a sine wave, amplitude, frequency, phase, etc. And when the object is created, you will assign all of these values so that they can be used by the get value function. And then your get value method is where all the magic takes place. So you'll see here, get value is a standard sine wave function. So amplitude times sine 2 pi frequency t plus the phase plus your DC offset, etc. So whenever you call this get value function, it will go and perform this calculation and return the value that you want to print out onto the driver so you can drive your stimulus to this real value. And all of the wave functions will look very similar to this based on whatever their mathematical function is to get their value. And then you have, in addition, you have a these modifier methods, and I just showed set phase here, but you could have increment phase, you could have increment the frequency or set the amplitude, etc. And you can use these modifier methods to modify the properties of this object after it has been created, which is very valuable, and I'll show examples of that in upcoming slides. So in this next section of the paper, we'll talk about the agent itself. So we have our function generators. Now we need a sequence item that we can encapsulate this function generator so that we can actually drive this out using the agent. So you'll see that all of the properties that you require for all of your function generators are defined here. So if you have a value that you need to tweak, then you add it here as a rand real value. One thing that's interesting is the step time property. This is used to control the sampling time of the get value method calls from within the drive task. So just remember that this is also a rand real value, and we'll get to that here in a minute. Next, you'll see there is a handle to the function generator object. This handle in the sequence item allows us to modify its properties using those modifier methods after the sequence item has been created. And finally, you'll have this enumeration here at the end, where you can randomize the type of function generator, whether it's just simply setting the value, or in this example I have an RC function or a sine wave, whatever. So in this way you can randomize what function generator type you want to see, or you can strain this however you see fit. So further down in the sequence item, we have some other methods here. We have some helper methods that allow us to create these function generators. So you have this first one is just setting the value. So it just returns a value gen object of null. You can use this in the drive task to say, oh, I'm not actually processing information, just set the value and exit. So this is kind of a handy little method to call here. And also I gave an example of an RC. So I create an object, and I assign the properties with whatever random values are in the sequence item, and then I pass the handle into the sequence item value gen object so that we can use it. And then you'll see we have a post randomize method, and based on the function generator type, we can go and call these little function generator methods here. So after you've randomized, it will go and create the object, and then from there you're good to go and send this to the driver. All right, so with the sequence item in place, now we can move on to the agent interface. So how are we going to drive these sequence item values out to the DUT pins? The first thing I want to note is that the net type is flexible. So that's what this tick ANANET T is, and this tick ANADATA T. My paper from last year, that was kind of the precursor to this, I went into a lot of depth of why I have these flexible net types, and you can go look at that paper and see how that all worked there. But for the purposes of this presentation and this paper, just assume that tick ANANET T and tick ANADATA T are just a scalar real value. It just simplifies a lot of this logic. So with that in mind, the first thing that I want to note is this little event here, this pin end event. So one of the things I ran into when I was trying to get all this working was I wanted to trigger an event whenever the net type changed. So you'll see that I have this little let statement here called ANANET flatten, and this is based on the net type. So in this case, all this let statement is it will turn your real value to bits using that real to bits system task. And then it's just a 64-bit packed array. And then I can use that value in an always block and trigger an event. And I found I had to do this because some simulators will allow you to use a UDN and it will trigger on anything changing, but not all of them do it. So by using this little let statement, I don't care what simulator I'm running on. So that was kind of the first thing I ran into. The next thing you want to know is I have a monitor for the receive side and I have a monitor for the drive side from the agent itself. So I needed a way to determine when the agent was driving and when I'm receiving data from the outside. And that's where a little bit of this magic here comes in. So I have this ad hoc drive clocking block event here, and that triggers the driving clocking block. And that gets triggered by the drive task, and we'll see that here in a minute. So every time the drive task drives out a value, it triggers this event, and it triggers this drive clock block here. Then I have my monitor clocking block, and it gets triggered on this pin in event. So every time the pin in event triggers, the monitor clocking block goes, and I use that later. So here's the little piece of magic. So the monitor to my receive side, whenever the driver has triggered this event, I do not send that transaction to the receive side monitor. I only send it to the drive side monitor. So I'm able to use these events to block off the things I don't want to see, and it helps me sort out what is being driven and what is being received. And finally, we get to the meat and the potatoes of this thing, driving the actual value out to the DUT. Things are starting to come together finally here. So we have a drive task. So the driver and the agent, all it does is trigger this drive task. So it doesn't actually do anything. The driver just calls this method. So then we send that data to the drive side of the monitor. And then we put this item in a mailbox. So I don't use system Verilog mailboxes very often. It was just one of those things I kind of had on the shelf, but this was a case where it was a perfect place to use it, so I did. So the driver puts this sequence item in the mailbox, and then it exits. So in terms of what the driver sees, it's done. It exits immediately. And the reason for that is I didn't want the driver to care if it was driving something that ran forever, like a sine wave, or something that ran for a long determinate amount of time, like say an RC function that decays to a final value, versus something that exits immediately. I wanted the driver to just exit, finish it up, and move on to the next thing. And I'll go to an example of that here after this, but just keep that in mind. So with the driver bailed out, it put this thing in the mailbox. All the real magic happens in this forever loop inside the interface. So it waits for an item to appear in the mailbox. And when it does, it's no longer null. It will copy that item, and then it will go and call the getValue method from its function generator object. And then after it gets that value, it will go and drive the pin and then wait for the step time, which is that value we had in our sequence item. So you can randomize your pound delay here to determine accuracy versus simulation speed. So that's where you control that little knob. And this thing just sits here, and it just loops back and forth around and around and around forever until it either finishes or until you get another item in the mailbox. At which point it will go and process this again and keep on looping through. So that was a lot of work. So we finally got here where we can do something interesting. So now we've got our function generator library set up. We've got our sequence item set up to go and configure it. We have our driver and the interface set up so that we can actually drive it to the pins. So now we get to the point where we can actually make a sequence and do something with all this stuff. So how do we start? So we go and create our sequence item, and we've already set up all the randomization, etc. So we start the item, we randomize it, we tell it in this case, oh, I want a sine wave. So we can set our constraint here. And then we're done. In terms of the agent, it's finished, the driver's done, everything's done. But in the sequence, you still have a handle to the function generator object itself. So you can come in here at the end of towards the end of the sequence, and you can go and use your modifier methods to change things. So in this little example, I have I'm increasing the frequency, I'm decrementing the frequency, I'm increasing the amplitude, I'm decrementing the amplitude. And you can see down here, the sine wave is doing just that. It's increasing in frequency, and then it's decrementing in frequency, then it's increasing in amplitude, and then it's decreasing in amplitude. So this is just a simple example of changing this one function. You can also stack these, so I don't have an example of that. But say, for example, right about here, I create a new item of type, say, RC function. So say I want the sine wave to run for some period of time, and then I want it to shut off and decay to 0 using an RC. So say that happens right about here around time step 8,000. So what would happen is the mailbox would get this new item called an RC function generator, and it would immediately start processing that and kill the sine wave. And then you just see this RC function decay to 0. Just like something like this. It would look a lot cleaner than that in real world, but I'm doing the best what I can with this little highlight tool. So yeah, then you can see that decay. So you can not only modify one function generator type inside of a sequence, you can stack these and create very interesting combinations of these things randomly, if you desire, to do some really complicated analog stimulus very easily. So this leads us to the final part of the paper that covers randomization issues. So as you'll notice in the sequence item, there are a ton of properties for all these function generators, and all these are reals, so there's no simple bits or anything like that floating around. Every application is going to need something a little bit different. So I wanted to make a generic agent and allow the user to modify this on a per pin basis without having to extend the sequence item class for every pin just so they can tweak something. So to go solve this problem, I started looking back through papers from previous DVCons and other conferences, and I stumbled across a paper by John Dickel that outlined this idea of randomization policy classes. To summarize his paper in just a couple sentences, it utilizes the concept of global constraints. And global constraints, as defined by the system Verilog LRM, are when an object member of a class is declared rand, all of its constraints and random variables are randomized simultaneously along with the other class variables and constraints. So what this means is you can put your constraints and other class objects and put them into a rand queue inside of your sequence item, and all of those constraints will be considered when the sequence item itself is randomized. What I found after looking at John Dickel's paper and going through all that stuff, I found it still wasn't exactly what I wanted. What I wanted was a way of generically constructing these constraints and using them in sequences downstream. I had this common problem of I needed to set ranges or restrict certain ranges of values or restrict certain specific values, or I wanted to see a specific value hit more often than others. And this led me to an idea that I call a policy builder class. So it extends from the policy based class, which we saw before. And inside, it has a queue of this policy builder T struct. So I have a queue of these things, and this struct just has a low and a high value for specifying ranges. It has a value for specifying set ranges. It has a enumeration called value type, which allows you to say whether it is a single value or a range of values that you want to cover. And it also has constraint type, which is this a constraint that allows certain values, or is it a constraint that prohibits certain values? So with the add method, you can go and add these policy builder structs to the policy builder queue. So from a higher level in the sequence, I can say go allow this range of values and go prohibit this range of values and go allow this single value, but don't let it be this single value, right? So you can stack all of these policies on top of one another using this method. But there's one thing to remember. So the way this works is all prohibit policies are considered. So if you say it can't be any one of these in number of ranges, it will consider all of those when it goes and constrains the value. But only one allow policies allowed at a time. So what this means is that when you randomize this case and you have multiple allow ranges or set values, it will just randomly pick one of them, which is probably what you wanted. So you have this method called get allow selections. So when you call this, what it will do is it will go through the policy builder's queue and look for all the policies that are allow policies. and it will go return this, return a queue of these values, indexes out, so that you can go and walk through these and pick one. And I don't have an example here, but in the paper, I go show how you can use this policy builder class to construct generic policies for each of the properties in your sequence item. It goes into real low level detail of how exactly to do that. So for the purposes of time, I didn't put it here, but the paper has some good examples. All right, so finally, we're putting all this stuff together. So this is kind of a real world example, and it shows an RC function generator. This example only has constraints for the value, but all the properties can have these associated policies that I described earlier. So you can tweak whatever you need to. Just in this case, I just set the value. So inside of your agent configuration object, you can set up a default policy, which I didn't describe here in the slides, but it's also in the paper you can go look up. So you'll see here I have this item config.policy, and then I have this value p policy that I'm appending here. And so I will concatenate these two queues of policies together, and it will be set to the sequence items policy. So when you randomize the sequence item, all of these policies that we're adding here will be randomized, and all of those constraints will be applied to whatever the value is that you're wanting for your RC function when it gets created. So let's see what we're doing here. So I have created a new value p policy. And I always put underscore p just so I know it's a policy, syntax thing, whatever you want to do there, just for me so I know. But in this case, I'm adding a set policy of a value of 1.2, and I want this to be an allow. I'm also adding a range from 0.7 to 0.9, and I'm also adding a prohibit policy of 0.75 to 0.85. So the value that will get spit out will either be 1.2, or it'll be 0.7 to 0.75, or it'll be 0.85 to 0.9. And you'll get that randomly whenever you go and create this function generator object. So this just shows that you can, from the sequence level or the test level, you can go and change all the different properties of this thing where it matters, where you're creating the sequence. And if you have default policies, you can use those by default, or you can simply not include them and use your own generated list. So it gives you full flexibility at a late stage in the game, and the agent itself doesn't have to care what you want to do with it. And finally, we get to the UPF pin agent. So we did all this stuff for just driving regular analog pins. And what I found is that the UPF agent can use about 99% of all of that code. It's almost identical. The only two differences are that the UPF has a set net type, which is that UPF supply net type, which is specified in the UPF package. And also the fact that UPF pins cannot be bidirectional. So this causes the agent interface to be a little bit different to handle this in the clocking blocks and in the interface drive function. So the main thing is when you go to your test bench interface level and you're actually connecting your supply pin agent interface, you'll notice that the supply pin agent interface doesn't actually have any pins at all. And that's because of the bidirectional nature. I couldn't set that pin as an input here and drive it as an output. It would actually just fail because the UPF net type, I believe, is just a structure. So what I did instead is I have an internal variable called supply pin. And at the top level interface level, if I'm driving the supply pin from the DUT, or whether the DUT is being driven by the supply pin, I'll simply assign those properties appropriately at the test bench interface level. And that allows me to have a bidirectional supply pin agent and while still following the rules of the UPF net type itself. So to summarize, use of these strategies allows one to build a standard UVM agent for UDN and UPF pins, and it allows you to use all the standard UVM verification approaches to both behavioral models and in co-simulation. The function generator classes encapsulate these commonly used waveform functions and provide you the ability to randomize and combine these into more complex functions. And finally, the randomization policy objects enable passing constraints from the test level and the sequence level to allow fine-grained control without having to extend the sequence functionality for each individual pin. So thank you all for attending. Have a great rest of your conference.